Hi, I'm Brandon Sund. I'm a security researcher at Tuta, and you're listening to Firewalls Don't Stop Dragons.
Hello, everybody. Welcome back to Firewalls Don't Stop Dragons. I'm your host, Kerry Parker. Today we have episode 394 for September 16th, 2024. Got a very interesting interview for you today. We're going to be talking with Brandon Sund from Tuta, the privacy-focused email company, among other things. They have other secure and private products as well. But they have recently rolled out something called quantum safe encryption, sometimes referred to as post-quantum cryptography. That's a mouthful. Basically, what we're saying is there is something that you've probably heard about in the news, or maybe, called quantum computing. It is a new type of computing that has kind of specialized purposes, but if we can get it to work, has a lot of implications for, among other things, potentially being able to crack modern encryption. And so this is, as always, as with these kind of technology things, with crypto, there's the cryptographic researchers who are creating these algorithms and code breakers who are trying to break them. And quite often they're the same people, because part of our process for creating these new encryption algorithms is also to have third parties really try to beat them up, like really try to break them. And that's how we prove through scientific method, with independent verification from hopefully unbiased third parties to make sure that what you're claiming is true. Anyway, so we're going to get into a lot of that today because quantum computers are an actual thing now. They are something that has been built. However, as we are going to see today, they've got a long way to go before they're a threat to even modern cryptography. So this is going to get technical, but I don't want you to get caught up in the really gross quantum mechanics physics stuff that we're going to kind of talk about tangentially here today. The really important thing, the really key takeaway from what we're going to talk about today is not the quantum mechanics stuff itself, not how quantum computers work, or even how they break cryptography. I think it'll be good to talk about that. But at the end of the day, kind of the bottom line is there's a lot of caveats to this. And this is probably glossed over in the media because quantum computers, while they do have a lot of potential, they're a long way from being a real threat, but they are advancing steadily and getting more powerful by the day. So it is something we need to pay attention to. And Tuta, to their great credit, is on top of that. And so Brandon and I are going to talk about this. We're going to run through some terminology. We don't stop to define all of them. So as usual, I'm going to try to define a few things, give you a little heads up before we get in there. So when you hear these things in the podcast, you'll know a little bit about it. One of the things we talk about is a qubit, which whenever I say that, I think of a classic Bill Cosby skit from the day about Noah talking to God and asking him what a qubit is. Now, these are two different types of qubits. The qubit we're talking about here is spelled Q-U-B-I-T. The old measurement called a qubit is spelled C-U-B-I-T, which I looked this up, and according to Wikipedia anyway, it is the distance from the elbow to the tip of the middle finger. So, in the old days, people didn't have tape measures laying around. So they came up with things like hands and stone, and kind of weight of common object kind of things and length of common objects to do, their measurements. So anyway, that when we talk about qubits, we're not talking about those qubits. We're talking about quantum bits, qubits. We briefly mentioned Schrodinger's cat. This is about a physicist named Schrodinger who expressed a concept to Einstein back in 1934 about this superposition kind of quantum mechanics thing that was highly theoretical at the time, where you don't really know until you observe something what its state is. And so the paradox, the idea is that it exists in both states until it is observed. I'll let you look it up. There's a link in the show notes if you want to know why the Schrodinger's cat thing is a thing. It's kind of a morbid thought experiment. But if you want to look that up, there's a link in the show notes. The other thing we're going to kind of dive into today is that cryptography, modern cryptography, especially public key cryptography, is built around math problems, a very specific class of math problems that are easy relatively to go one way, to maybe compute in one direction, but really, really difficult to go the other way, to undo, to reverse. It's prohibitively difficult. And by that, I don't mean it's impossible. I just mean that, let's say it takes me a half second to go one way, but it takes me a million years to go the other way. That's the kind of differential that we're talking about. And that's the basis for a lot of what we call asymmetric cryptography, public key cryptography, where there's two keys, one to encrypt and one to decrypt. But what we're going to find today is that the particular math problems that we have used for literally decades to do this kind of cryptography, these particular class of math problems may be vulnerable or much easier to compute with a quantum computer than with a standard computer that we have today. And in fact, the kind of the comparison that we're talking about here is, can we come up with an algorithm or some sort of a way to calculate something that's faster than guessing every possible answer? And guessing every possible answer is what we call brute forcing something. So if I said there is a gajillion possible answers to this question, and your only way to figure that out is just to try each of them in order until one of them works, that's brute forcing something. If you come up with a technique that would let you cut that problem down by an order of magnitude or two, in other words, a factor of 10 or a factor of 100, now you're really talking about you've come up with some way to attack this problem in a way that is faster than just trying every possible combination. That's the kind of thing that goes on when we're talking about breaking encryption. It's usually about finding some clever way to attack these math problems that make them significantly simpler than what we thought they were. Okay, a couple more things. We throw out some acronyms like NIST. I've talked about them before. That's the National Institute of Standards and Technology here in the U.S. I often say science instead of standards. Like I kind of get that wrong, but it is National Institute of Standards and Technology. We talk about some encryption algorithms. You don't really need to know this, but when he talks AES, that's Advanced Encryption Standard, or MD5, that is a Message Digest version 5. It's an old cryptographic hashing algorithm that's no longer secure. We don't really stop to define those things, but when those things get thrown out, that's what we're referring to. Okay, enough of that. Let's get to the interview with Brandon from Tuda. Brandon is a privacy and security researcher at Tuda. Tuda is an encrypted email provider based in Hanover, Germany, previously called Tuda. We've talked about it on the show before, but never had Brandon. Thank you for coming on the show, Brandon.
Yeah, thank you so much for having me. I'm looking forward to talking with you about quantum computers and all things encryption. Should be fun.
Yes. So it's something, it sounds straight out of a sci-fi, right? Quantum anything. It just gives it that, like, is that real? You know, it just sounds a little bit too far out there. But no, it's a real thing, sort of. I mean, I guess we're not quite there yet, which we'll get into, I'm sure, as we talk today. Mm-hmm. But it's a whole different thing. So let's start off with the basics. Why don't you tell the audience, what is quantum computing? Why is it so different? And what types of problems are these quantum computers better at solving? In other words, like, why are we building these things? Why do we need a quantum computer?
Yeah, for sure. So first of all, quantum computers, I mean, they're a new potential alternative to classical computers. So we're all pretty familiar with what a classical computer is. Processor with little transistors on it, and classical computers operate on bits. So these are our zeros and our ones. Classical computers were everything from the giant mainframe computers that NASA used to land things on the moon to like your phone, right? So we've already seen just in the last few decades the major jumps that classical computers have made. Quantum computers, as an alternative, they don't operate with bits. They don't use zeros and ones. A quantum computer uses it's called a qubit to store data. So a qubit, unlike the zeros and ones, it doesn't just have these two states, even though they're this linear combination. So in the physical world, qubits are going to be based on something like the spin of an electron. So a lot of times people will talk about spin up or spin down. And because these particles, all these particles that are used in quantum computing, they're so little, they're so small, the principles of quantum mechanics apply to them. So in a way that isn't the case with classical computers. And what's most important from this is the principle of superposition. So the state of a qubit isn't just spin up or spin down. with superposition, it's this, yeah, how would you describe it? Um, yeah, it's tricky.
Yeah.
Um, yeah, so it's not just these two possible base states. It's a superposition of it where it sort of exists in both states, in both spin up and spin down. So we prior to being observed.
Hmm.
So a lot of people you hear like stories about like Schrodinger's cat,
I was just about to say it sounds
or
like Schrodinger's cat. Yeah.
the double slit experiment.
Mm.
These we don't know if it's a wave or a particle before you observe it. It's similar. This principle of superposition is similar to that in the case of
Okay.
quantum
All right.
computers. So we don't know if they're spin up or spin down. Spin down. And when it's just a few qubits, it's really not that interesting. But as you scale it up, and ideally, this is kind of in a theoretical space. As it scales to a more to a higher degree, it reaches a point where we could possibly do something with it. We can start doing calculations. So rather than just, okay, either or 0, 1, you can start doing multiple things at the same time. So it's faster. And one thing with this is that's only possible if we are able to achieve, or physicists, computer scientists are able to achieve long-lasting quantum entanglement. So you have these qubits, right? One qubit on its own is not that interesting. It's random. So you observe it, is spin up, spin down, whatever. There's not a whole lot we can do with that. But as soon as you add more and more, physicists can go ahead and they can prepare these electrons, for example, in such a way that they're entangled. That means that these multiple electrons are going to exist in a state where if you measure one of them, you know the state of the other without having to observe it.
Mm.
So say we have electron A and electron B. And physicists were able to entangle them. We don't have any issues. This is like perfect theoretical example. If we were to take them apart from each other and move them apart from each other, and we only observe A, because they're entangled, we will also know the state of electron B. And as soon as you have this reliable entanglement, you can escape randomness. And once you can escape this randomness, physicists, computer scientists can start exploiting these theoretical descriptions as a means of making calculations. If you can't achieve and maintain this entanglement, then you have noise. It's not useful. So right now, the quantum computers that we have, they're big. They really do look like something out of a sci-fi movie.
Yeah.
Tubes everywhere. Everything needs to be super cold, super isolated. And we're still not able to really keep particles entangled for a very long time. True entanglement needs to be like absolute zero Kelvin. We can't do that.
Mm.
And also, you want to have zero external interference. So you don't want any sound. You don't want any other temperature. You don't want any kind of radio waves, frequencies, anything at all that can
Impart
impact the
energy.
state.
Yeah.
Yeah, because otherwise it'll throw it off. And because we're not quite there yet with these computers that we're like in early stages of developing, not weird, that's not something we're personally building, but big companies and governments.
Yeah.
The machines that do exist, they have a very high error rate. Because of that, you can't really do a whole lot with them yet. And then, yeah, you talk about, what are they for? One thing with these quantum computers, there isn't a general programming language in the same way that you'd say, okay, cool, we went ahead and we wrote a certain program in Rust or in Java or C, whatever. These computers need to be hardwired to solve specific problems.
Oh, interesting.
So one of the theoretical cases is that this could be used to break encryption. That's one thing that comes into a lot of discussions. And also being used as a means of simulating quantum experiments.
Wow.
Because with standard computers that we have now, classical computers, this is a little bit, it's more difficult. Yeah, and because quantum computers aren't processing all of this data in zeros and ones, they're able to represent both of these states simultaneously. So in the case of cryptography, they pose a threat because they're going to be exponentially faster, and they can be hardwired or they can be programmed in a way that would be used to attack certain fundamental problems that are used in the kind of traditional current forms of encryption that we use. The main example that people really go to would be RSA.
Yeah.
asymmetric encryption. And that's because these types of computers, these quantum computers, would be very good at solving problems like integer factorization or the discrete algorithm problem. And these are the bedrocks of RSA, of these asymmetric protocols. So while this is something that's still in development, it's still very early stages of development. I believe the current quantum computers that do exist that they've been able to get them to run what's called Shor's algorithm, which we can get to that later.
Mm-hmm.
They were able to find, I think for integer factorization, they were able to peak at like 15 or 35.
Bits.
And like at the number.
Yeah, like the number of bits of an
Yeah.
RSA key, I think, right?
And in RSA keys that people are using are 2048.
Yeah,
2048
minimum
bit
today. Yeah, right.
plus. Right. So they have quite a long way to come, but the fact that there's kind of a foot in the door, right?
Yeah.
So it has been shown that to a certain degree this is possible. So in the case of, this is kind of what our primary interest, in the case of cryptography, that has caused concern in the infosec space, cybersecurity space, because if these kinds of computers become more readily available, that poses a threat to pretty much everything that we do on the internet right now.
Okay.
I hope that answered the question.
Let me back up and see if I can kind of paraphrase some of that back to you and see if I get this right. So first of all, these things are big, probably extremely expensive, and not something that, a Steve Jobs and a Wozniak are going to be doing in their garage.
It won't be in your garage. No, you won't get away from interference.
Yeah.
No.
Right. So also, they're still in their infancy, but they're not science fiction anymore. We have shown that they're possible. We have functioning quantum computers today, but they are very, very, very simple. This is kind of like a digital calculator versus a Cray kind of scenario, right? They're still very, very early stage, in your example, they have cracked a 15 or 30-bit key, whereas the common RSA encryption keys, they are 2048 bits. In fact, 4096 is becoming more common. So there's a long way to go before these quantum computers are going to be breaking modded encryption because of the codes. The other thing I want to mention is, well, actually, let me ask you the question. You alluded to how this stuff works. Modern crypto, especially asymmetric crypto, which means there's a public key and a private key, these purpose-built, highly expensive, massive computers, what you're saying is they're hardwired for specific problems. It also sounds to me like basically what they're really trying to do is they're trying to create an encryption-breaking computer, because it does one thing.
Some might be being used for that, yes.
Yes,
but
yes.
We can't generalize that all of them would be, because they're very problem specific. There are companies that are working on this. Like we can assume governments are working on it as well, right? But companies like Google, Intel, IBM, Google and IBM in particular, you really see a lot of these pushes for more, like, what is they call it quantum supremacy, like who has the top of the line machine. And yeah, so right now, like, what they're doing isn't necessarily developing machines that are specifically oriented at attacking cryptography. They have possibly other problems that they're trying to use these for, or even like benchmarking to see, hey, cool, what were we able to achieve? So in the case of cryptography, quantum computers are particularly useful at attacking asymmetric encryption as opposed to symmetric encryption.
Mm-hmm.
And so, like, a little difference there. Asymmetric encryption, like you said, that is public-private key. So one of the keys is used to encrypt the message, and then the other key is going to be used to decrypt the message. But the one that encrypts it can't decrypt it, right? And with these types of algorithms, again, the famous one being RSA, they're built upon two specific types of math problems. Now, and again, these math problems being able to factor really, really big prime numbers, and then discrete logarithm problem. And currently, these numbers that are being used for keys, they're big enough. So with a classical computer, there's not really an algorithm that can break it in a reasonable amount of time.
And when you say a reasonable amount of time, we're talking years to centuries, right? I mean, in some cases,
yes.
Right?
Yeah. If you're going through and you're using if you're doing this properly, then yes, it should take a long amount of time. We're talking years, decades, hundreds of years, right?
Yeah.
But one thing with it is, or one thing that's kind of worth noting with, in the case of cryptography, when people talk about like a reasonable amount of time, or if they say a crypto system is broken, what they mean is someone found a vulnerability that is faster than brute forcing it.
Yeah. Right.
So even that, like there can be someone might find a vulnerability, but cool, instead of taking 2,000 years to decrypt it, it takes 1,500, right?
Yeah. Right.
So there's kind of this, yes, something could be considered broken, but then determining real like what is the legitimacy of the threat. So with classical computers, we can't really do this. And in the case of quantum computers, if it can run Shor's algorithm, would be able to break RSA. There was actually a study by the German government, and they said it would take 20 million physical qubits in order to break a 2048-bit RSA key in 8 hours.
Wow.
And we are not
20
there
million. And we're currently at how much? 15 or 30?
We just hit the 1,000 qubit mark in October of 2023.
Wow. Okay. Yeah.
And that's these early scales. So it has some work to do before it's really going to pose an immediate threat to our current crypto systems.
Right. Okay. So again, to paraphrase, basically the way modern RSA encryption works is it has a certain type of math problem, a certain class of math problem. In this case, it's factoring large numbers, the factor of 2 primes, which turns out is really hard to do in a short amount of time, unless there's a bug somewhere, as you said, a vulnerability you can find.
Correct.
So it's really easy to do, but it's really hard to undo without knowing the key, which is the whole point, right? Yeah. So
that's your trapdoor function. It's very easy to go the one direction, but getting it back the other way, good luck.
Right. All right. So how long have we been doing this? Because I've heard about quantum computers for a long time, and I'm not sure. Like I'm not sure the actual history. Like when did we go from theory to concept? Like when was the first time we had like a working one? Give us a little taste of the timeline of evolution of quantum computers.
The thing with quantum computers, first of all, quantum computers, the idea is that it's a practical application of quantum mechanics. Quantum mechanics is old.
Yeah.
So that's shortly after kind of thing. One thing that we did find, like some kind of early dates, we really saw things picking up and that momentum really beginning in the 70s. In 1973, a theorem was created that was able to show that qubits would be able to store more information than classical bits. So that's kind of the ball starts moving. In 1980, Paul Benioff, I think that's how you pronounce his name, he published a paper, this was the first quantum model of a computer, which that kind of set the possibility for like, hey, this could be a thing. 5 years later, researchers at Oxford started describing the first universal quantum computers. Things started to move forward in the 90s with the discussion of quantum entanglement being used as a means of basing or kind of creating secure means of communication. And this ended up growing into what's called quantum cryptography, which is not the same as post-quantum cryptography or quantum safe cryptography. Those are different things. Quantum cryptography is going ahead and using these principles of quantum mechanics as a means of encrypting data. So it's something else. And for cryptography, what really kicked things was in 1994 when Peter Shor published Shor's algorithm. And this was also, NIST started organizing quantum computing workshops. A year later, the word qubit was really coined, and things started moving from there. Yeah, in 1997, people started working with, they're called nuclear magnetic resonance quantum computers. And these were popping up at research universities, so MIT, Stanford. And yeah, in 2019, IBM came out with the first commercial quantum computer. It's called IBM Q System 1. And that was like the first, hey, this is a thing. It's not sci-fi anymore.
So step away from the heavy duty stuff a little bit. To summarize, basically, we've got a new type of computing that it's extremely expensive to do, that is very much in its infancy, that may theoretically someday be able to, potentially years down the line, may be able to break current cryptography. So,
Correct.
uh, if viable quantum computing is really that far off, if it's really, it's not sci-fi, but it still seems like it's many, many years from being, a threat to modern cryptography. Why is it so important to implement quantum computing resistant technology now?
Yeah, so there are a few reasons for this. One thing is, regardless of a quantum computer, say quantum computers never really came to fruition. They never get out of this like early stage. We still have a theoretical, like a white paper that shows a potential weakness to these systems. So if there are ways that we can improve them, and in the case of post-quantum cryptography or quantum safe cryptography, that is swapping out these possibly potentially vulnerable core problems that the cryptography is based on for other types of problems that wouldn't be susceptible to the same attack. So just from this improve it because we could stance, it's nice. It's polishing it, right? But from a more practical standpoint, one thing that we do see and this kind of comes more towards my work, toward what we're doing at Tuta, is some of the mass surveillance that is going on with governments.
Yeah.
So there is a practice called harvest now decryptolator, and it's a type of attack where basically there are lots of, like, everyone is using encryption every day on the internet, different forms of it, but encryption is there
Right.
to protect your data. But all of this data is being vacuumed up, right?
Mm-hmm.
And so we don't know the full extent of this because there are intelligence agencies doing this. There are data brokers that are doing this to a certain degree. And one thing is, yeah, so we don't know the full extent to which this is happening, because in the case of like government surveillance programs, this is classified information. This is something that we just don't have access to.
Right.
But there are certain things that we do know, right? So we have the Snowden revelations, for example,
Yes.
in 2013. One thing that we do know, the NSA has data centers all over the United States. One of the really big ones is in Utah. It's just called the Utah Data Center. And it was finished shortly afterwards. It was finished in, I think, 2014. So like right after the Snowden revelations. And it's estimated that this data center alone, so this data center can hold between 3 to 12 exabytes of data. So an exabyte is 1 million terabytes.
Wow.
And I was kind of curious. I did a quick search just because I was interested how much data Google might be storing, because we know like a lot of people use Google to store their stuff. And the estimate for Google is that they're storing 10 to 15 exabytes worldwide. So the NSA has, just at this one data center, damn close storage capabilities. So what you need that much storage for, I don't know, but it would lean some kind of degree of confidence that there is some kind of collection of encrypted data, because there's not that much unencrypted data, to my knowledge. I would hope not.
Right.
Anyway, and so we know that this is happening. And another thing with that, a few years ago, I think it was in 22, the U.S. government actually put out they made an official roadmap for different government organizations and also private organizations as a means that they could follow for becoming quantum safe. The idea being, okay, cool, we have all of this data flying around, which is currently encrypted and relatively safe or relatively safe. But in the event that a quantum computer does come into fruition, somebody has one, and they can start decrypting all of this previously secure information, that poses a huge threat. I mean, your online banking is there, right? So that's one thing. That's small potatoes stuff. Corporate data is being sent encrypted. So if you can break that, you can start stealing corporate secrets. Government data, military data, all of this stuff is sent with encryption. And if that encryption is undermined, then that data is open for grabs. And so the idea is it might not be there yet, but the possibility of it is frightening enough that we should take action if possible. And that's what researchers are doing in post-quantum cryptography.
So yeah, all these bits are flying, right? And they're flying oftentimes through public data points, either or through controlled nodes with, layer 3 or some of these other backbone providers. If as Snowden has said that they've got taps on some of this data and they could just siphon off copies of all this data, yeah, it's encrypted now. But if they come up with a computer in 10 years that could do it, is there something you did today that if they learned about it 10 years from now, you would have a problem with, right? Yeah, I think so.
Well, I mean, something like that. That's a big there's a common discussion when people talk about like in the privacy space. People say, "Hey, what do you like?" People will say, "Oh, if you have nothing to hide, you have nothing to fear," or something like that, right? Well, the problem with that is like what you said. Okay, you might not be doing anything illegal right now, but in 10 years, 20 years, what you're doing now could be considered illegal,
right,
or depending on changing political situations or things like that.
Exactly.
So it's important that kind of data privacy is maintained.
How long have we been working on post-quantum crypto? Like, there's one thing about cryptography that I think a lot of people don't get it because, we're not researchers, is that these guys work on this stuff all the time and they're coming up with new algorithms all the time. They're improving algorithms all the time. Sometimes they're just making the key sizes bigger, but a lot of times they're coming up with new techniques to solve problems because there are vulnerabilities that are found and they're beating these things up over the years and trying to find ways around them and to make them better. So how long since someone said, hey, we might be able to make a quantum computer that could break this stuff, did someone else say, maybe we need crypto that is resistant to that? So how long have we been working on that, and what does that math look like? What did they do differently to make it resistant to the powers of quantum computing?
Yeah, so I mean, with that, as soon as Shor's algorithm was really proven to point out these weaknesses in current cryptography, like that's work started. Like this paper came out, somebody read it, and there was a hard oh shit moment. But what we're talking about now with post-quantum cryptography, and most recently, like this is something that Tuta has been working on with like our own post-quantum or solution for quantum safe cryptography, is actually in response to NIST launching it was a call for the official title was the post-quantum cryptography standardization.
Yeah.
And this started in 2016.
Okay. And
they have announced their selections, which types of encryption are going to be standardized.
Right,
and
recently. So in other words, like 8 years of this process.
Yeah, and that was they went through, and this was announced last month. This was in August where they announced this, and two of the main ones being Kyber, Crystal's Kyber, and Crystal's Dilithium.
Dilithium. That's a Star Trek reference. Yeah. The other one's a Star Wars reference. Yeah, interesting mix.
Okay,
but yeah.
Perfect. I'm not a Trekkie, so I missed it.
Yeah.
But yeah, so the idea is that we know that quantum computers can attack RSA. So what people went ahead and tried to do was move forward and replace these problems that like RSA was based on. So all of these solutions are similar to a degree in that they're avoiding factorization of these primes.
Yeah.
And then they're trying not to use the differential logarithm problem. So instead, what they're doing is they're using other problems that are considered hard. And this, like the hardness of a problem is just that there is not a known algorithm that can break it faster than, like we said earlier, faster than a brute force. And the example with Kyber is what is based on what's called a learning with errors lattice problem, modular lattice problem. That's actually what it's called MLChem. In NIST's the standardization of Kyber is called MLChem. It's module lattice key encapsulation mechanism, I believe.
Okay.
Big words.
Yeah.
And a lot of the other candidates in this process were also using lattice problems. And what these are is, so like these module lattice problems, they're able to replace the prime numbers, discrete logarithms, and they kind of look like these problems. They look like linear algebra, but they're introducing errors. And these errors, they're little numbers, and the introduction of these errors causes these equations to be much harder to solve. So learning with errors problems, they look like RSA, but you can't optimize for these kinds of algorithms with a quantum computer at present. We don't know of a way to do that. And this is something that throughout this standardization process, as soon as, you have different teams, different like research universities or research groups, they go ahead and they propose specific new algorithms that's potentially quantum safe. And then once they are proposed, everyone in the cryptography space proceeds to just try and break them.
Yeah.
And so this stress testing, this public stress, and it's what is really, really important is that this stress testing is public.
Yeah.
And as one is, it's a means that everyone can trust the process. The process is transparent. And in the case of cryptography, it shouldn't, if you have a secure algorithm, it shouldn't matter if someone knows what that looks like. As long as you have your secret remains secure, the encrypted data, it should be secure.
Right. Security by obscurity is never a good plan.
No, it is not. And that's one thing. There's what's kind of interesting with it is there are, like, you can talk about, there were kind of some, as NIST is based, I believe it's based in the United States.
Yep.
And one of the things with this is there's kind of there's concern that, okay, if it is based there, what is the role that like the NSA might have in this standardization process? And are they building a backdoor into it? That kind of these kinds of questions come up, right?
Well, let's be clear. They didn't pull this out of thin air. This was not a tinfoil hat thing. There was a case where the NSA was found to have picked either a known weak version of some algorithm or something that they talked NIST into. I think it was NIST, or maybe it was RSA. Maybe it was RSA they talked into doing this, but they promoting a known weak encryption standard. So that was actually what the question that keep going, but I think you're going to answer my question. But how can we trust this process?
Yeah, and, one thing that you see with it is first it's public. You can go through and you can look at this stuff. I mean, the average person at home, you're not going to be able to go ahead and sit down and be like, oh, okay, cool. I'm going to do some cryptanalysis with my evening, like have a beer and
carry the two. I see what they did there. Yeah.
Yeah. So while that's not necessarily feasible, what is important is that NIST themselves, they're not developing these algorithms, and they're not the only ones blindly stamping review. So one thing that actually happened in like this current process with Kyber is there was kind of a controversy flare up with Kyber 512, which is kind of funny when you look at it. NIST went through and basically claimed an incorrect security level for Kyber 512. And this kind of led into that suspicion, like what you're talking about. We're like, oh, did they do this on purpose? Which we ultimately don't know, right? We don't really think so, because if they did do it on purpose, it was so sloppy. Because really, it was this was caused by basically a typo. So it received a higher level of security rating than it actually had, and it was something like swapping addition and multiplication. So somebody hit the wrong button, and this is something which was quickly pointed out by the cryptography community. Like, this again shows that why it's so important that this stuff is public.
Yeah.
You say it's not. So say just all of this stuff happened in a back room and no one noticed a typo, then you have something broken out there. One thing you can also see with this isn't the first time that NIST has had these standardization processes. This was something with when things moved from DES, so data encryption standard, to AES. They did a similar thing where they went through and it's okay, cool. There is public call for new encryption algorithms. So all of the postgraduate researchers, everyone who's looking for tenure publications, they get started, right? And one thing, Bruce Schneier, for example, he came out after that process. He was he proposed, I believe it was called Two Fish, was the name of his submission. He came out publicly and said that he has nothing negative to say about NIST or these standardization processes. And if you follow his blog, he is also quite political in the privacy cybersecurity space. So it's not, you can kind of trust that it's not bootlicking. Like he's a valued, his voice carries some weight. Yeah, and something else that's kind of interesting with it is, again, with this, you talk about like security by obscurity. There was something kind of weird, I think it's interesting anyway, with these different crypto suites. With AES, there was a point when everything was standardized that the NSA, there were two cryptography suites. There was Suite A and Suite B. Suite B had all of the commercial standards that we are using. Suite A had stuff that was not publicized. This was stuff that they kind of kept. It's interesting. Like it is classified. You can't look at it. Um, but it's an interesting happening that happened.
Yeah.
It's kind of interesting. And yeah, currently there's what we have is it's called the Commercial National Security Algorithm Suite 2.0, and that includes Kyber and the ML-Chem standards. So with this push that the US government has had for trying to get more organizations to become quantum safe, we already see that Kyber and these algorithms are being included in new standards, which it being publicly posted and everything, we know that from what we have seen, these are currently the most secure algorithms that we have. Of course, that can always change in the future. You never know. Someone might come out and find
The next short's
an
algorithm, right?
that can solve it. Yeah, so that's always a possibility. So the idea is that we're people in the cryptography space, tech companies, security professionals. They're working on the best knowledge that we have at the time.
All right, so that brings up another point, and that is, as people should be seeing from this conversation, is that these standards take a long time to develop and vet for good reason. We beat these things up a lot, and I think even some of the final contestants for the NIST approved ones, there were four, and then there were three. Like at the last minute, one of them, somebody found a vulnerability, and the last one, it was nixed. And so this vetting process is very, very important. And I know any cryptographer worth their salt will say you never roll your own. You always go with the tried and true.
No.
So that being said, should we be wary of moving to these? Are we betting everything on these new algorithms, or are we somehow like layering them like an onion and combining them, like getting a little bit of, keeping the old and some of the new, like double encrypting or something? And then I know there's kind of maybe orthogonal things like perfect forward secrecy and things that we can do with our encryption as well. And I know you guys, the reason you're here on the show is you guys are rolling this out. So like, what are you guys doing? Are you giving up on the tried and true and going straight to these new ones, or how should we be incorporating and adopting these new ones when we've got the tried and true ones, and especially when the computers are so far off from being real?
Yeah, so that's a cool point because like you don't want to we're not throwing the baby out with the bathwater. So with TutaCrypt, that's the recent release from our service from Tuta, and it's a combination of elliptic curve cryptography and post-quantum cryptography, in that case, Kyber. So what we're doing is we're having this combination. And of course, because we never know we don't know what happens tomorrow. We don't know what happens in the next week or the week after. But we do know that we currently have these secure algorithms that we can use, and then we can put something on top of them. So like you talk about the onion. So what we are doing is we have elliptic curve. And if say there is a quantum computer that is going to try to break what we are doing, first it has to exist. Right. It has to break elliptic curve cryptography.
Yeah.
Then it has to break Kyber. Then it's serious. So what we're trying to do is go ahead and use these hybrid models. And that's not unique to Tuta. This is something that any company that's really working honestly in this on presenting quantum safe algorithms, they're going to be making some kind of hybrid model exactly for this reason.
I think Signal did that too.
Signal did, yes. Signal, I believe, was the first company that came out with a post-quantum encryption solution. And I believe Apple also did this with iMessage or with Message. But yeah, Signal was the first. And one thing that we're also trying to do, this is something that Signal has, is perfect forward secrecy. What perfect forward secrecy is, it's the ability to protect your data in the event of a key being compromised, your encryption keys being compromised. So say your long-term key gets compromised. If you have perfect forward secrecy, that means it's not going to be possible for someone to go ahead and decrypt your past messages. Because otherwise, if that's possible, someone gets that one key, they have everything.
Right.
That's not what you want. So at present, TutaCrypt, Tuta's post-quantum or quantum safe encryption solution for email, is only providing partial perfect forward secrecy. This is something that we are going to continue with in the future, to continue developing in the future. This is something our crypto team is working on right now. And so right now, if a sender's key is compromised, your data is fine, can't be decrypted, right? But should an attacker be able to compromise a receiving long-term key, then things get dicey. Past messages could be decrypted. So what we're doing is taking a variant of the Signal protocol, similar to what they've rolled out, and that will then be integrated into the TutaCrypt protocol as a means of providing perfect forward secrecy. Yeah, and so the idea then is that this is then quantum safe, and this variant would provide secrecy, meaning that, say, an attacker were able to compromise all of your keys at some point, they would only be able to read future messages. So if you knew this compromise happened, you could say, okay, I'm out. And you don't deal with it. And then also keys are rotated, they're continually refreshed to prevent that, the ability for future messages to be read.
All right, so this sounds really complicated. This sounds like the kind of thing that only, certain companies, well, they'll actually back that up, because a lot of companies are probably going to come out. It's like all the companies that say we've got military grade encryption. That drives me nuts. If there's one thing that triggers me whenever I read, and it's usually an immediate turnoff, is somebody who claims they have military grade encryption. Like that, the fact that you even said that just bothers me.
It's a terrible phrase.
It really is. So how hard is this to roll out correctly? And where are we going to see it first? Obviously, it sounds like you guys are doing it, and Signal has done it. And then where's it going to show up last? Like I'm thinking like cheap IoT devices, for example. I
don't think those are ever going to be encrypted by default. Let's be honest.
Yeah. Okay. Probably not. So how long is it going to take to roll this out, and how hard is it going to be to do correctly?
It is a lot of work. This is something that for us, and Tuta is a small team. We just hit today, actually. We just had our 30th team member join. So Tuta is small.
And congrats.
But we were able to implement this. But it was also something that we put as a primary goal, because we do, as a company and then as privacy activists, we do see and take seriously the potential threat of quantum computers. So for us, this was something important to sit down and do. This was also something that we developed in tandem with the university. We don't have university cryptographers just sitting on in our office writing out crypto. That's not how it works. So this was a long-term research project between it started when Tuta was still Tuta Note. It began there, working with the University of Wuppertal here in Germany. And so this originally began as a means of first going ahead, and we wanted to develop this post-quantum encryption, not mainly, but to develop a quantum secure cloud storage system. That was the original grant we received to develop this with the University of Wuppertal. But we've also integrated that in for us, for email, for calendar sharing. And again, this quantum safe algorithms for email, you're going to have it secured at rest. So on your servers where it's not moving, where there you only need to use AES, which is symmetric. So AES 256 is fine. But in transit, then you're moving with you're using asymmetric encryption. So then it's important to have this quantum safe. I think bigger tech companies, I would hope, because a lot of those, like Google, for example, they have the money to build these machines, but whether or not they have the interest in developing these quantum safe solutions to them, that remains to be seen. I think you would see things like this being pushed. I mean, it's a money thing. It's a money issue, right? So I think you'll see things within the intelligence space, the military space, will jump on this because they can say, this is an issue of national security budgeting, right?
Military grade encryption. It's obviously the best.
Yes, it's military grade encryption. I think that's something that they will be able to employ or to deploy faster, or there will be more incentive to do so.
Yeah.
Because I think one thing you see with working in IT departments at companies, they tend to be kind of on a lower point when the trickle down of budgeting goes. They may not receive the support that they really should. Yeah, as far as who's going to get it first, I mean, I think the military will get it first. Privacy companies are working on it. This is something that we're doing, and I think the fact that Tuta was able to develop it with a small dedicated team shows that this is something that anyone can do. But yeah, there are definitely certain difficulties, or it's not something that should be done haphazardly. One thing that's very important for, say you have an existing system and you're looking to migrate your encryption from just traditional classical, the encryption that we have now,
Yeah.
to quantum safe solutions is, and this is something that we are working on at the moment, is key rotation. So if you go ahead and you've been using these other algorithms, which every other companies are, and you need to go ahead and transition in such a way that users aren't going to lose access to any data. Otherwise, congratulations, it's extremely secure and no one can
Right.
access it.
Right.
Like, it's so secure, I can't access my data. Great,
Correct.
that's useless. And so this is one thing when Tuta first rolled out our post quantum cryptography. It's initially only available to new customers. So if you create a new Tuta account, it's using that. It's using quantum safe
Hmm.
encryption
Hmm.
from the get-go. You're ready to go. And this is one thing that we did receive a lot of community feedback about, was like, hey, I'm a long-standing user. When do I get it? And yes, this is something that does take time, and it takes time because we want to do it right. If going through and making this transition, if there is you're not allowed to have a bug because people will lose access to their data.
Hmm.
So this is one thing where we are currently working on it. This is something that we are already testing internally on personal accounts, rotating these keys out from older accounts, which were using the older forms of encryption, to the quantum safe encryption.
So the issue is migrating the existing encrypted data from the old techniques to the new techniques. Which is why it's easier to start with new subscribers, but old subscribers have a.
Correct.
Okay, gotcha.
Correct. And one thing, there was actually, it's not necessarily related to quantum encryption, but one thing that kind of shows the importance of doing this was there was a data breach. I don't remember the year it was, but I believe it was I think it was the Ashley Madison data
Ooh,
breach, where they had a bunch of password hashes, and they had shifted at one point they had switched their hashing algorithm to something that was more secure, because originally they were using MD5. Well, the problem was some of those were still there.
Hmm.
And so people were able to go ahead and crack those.
Gotcha. Yeah.
And so this is something that while we do have these older, like, we're not using MD5. Don't get me wrong. Don't misunderstand that. We're
Good.
not
Okay.
using MD5. But just in the sense of, we're trying to go through and get existing customers moved over into the current, like, this up-to-date quantum safe encryption standard as a means of preventing that. Should quantum computers come into existence and that older form of encryption be faulty, we don't want that lying around. We want all of that data to be secured. And so it's also something that companies are going to need to keep in mind when they're trying to migrate these things.
Gotcha. All right. So on the flip side of this, who is going to be able to afford the machines that can break the current crypto? Who's going to be able to afford a quantum computer? It sounds, from everything we've talked about, this is not like, I mean, when the first days of computers, like, there was ENIAC and some of the ones that were room-filling computers that were only available to governments and large colleges or whatever, or universities. This doesn't sound like it's going to follow that progression. I don't see us having a personal quantum computer in our home to replace my Mac Mini anytime soon. Is that, am I getting that right? Or is there ever likely to be the point where, yeah, this is going to be what's going to be our desktop in 10 or 20 years?
I mean, we don't know, right? So on the first hand, I would love to have a quantum computer in my living room that I can run Doom on. Why not? But immediately, no. We're not at a state where this is going to be just a regular consumer device. The places that are going to have them are government institutions. Universities will have them to a certain degree, and then these massive tech companies that are developing them. But as far as smaller consumer grade quantum computers, I don't see something like that being a thing in the foreseeable future. And I mean, we're talking about even these larger quantum computers that could be used for breaking cryptography, these huge research machines that we're talking about. Something like this is something that's still considered to be decades away. So, we're not even to, like, the mainframe point yet. But at the same time, like, we can't see the future. And I mean, when I was a kid, I didn't expect to have a weird cassette tape sized thing in my pocket where I could watch like videos of cats.
Right,
That was
right.
not on my radar. So
Sure.
we don't know.
Yeah.
But most likely this is something that's not, it's going to be something that only people with very deep pockets are going to be able to use.
Okay, so what about the political aspects? We've talked a lot about the technical aspects, but there's a political aspect to this as well. Like, how do you think the top intelligence and law enforcement agencies are going to respond to the stronger encryption? Have you noticed, for example, I mean, have you gotten any notices from the U.S. government or your local governments? Actually, not even sure where TUTA is headquartered, but
We're in Germany.
okay, so that's different. But have you gotten any pushback? Have you noticed any political pressure to, yeah, let's not rush this out just yet? Who knows what the NSA can break or thinks they could break in the near future, but they probably don't like having to come up with something new.
We haven't received any formal pushback about this, and that's one thing with even with standard encryption. I mean, there is when you look at like what currently exists for encryption possibilities, this is something that you publicly see politicians, really regardless of which country you're from. That's not true. That's not true exactly. But you do see there is political pushback against encryption.
Sure. Yeah.
A lot of times people will say, "Oh, what do you need this for?" They only want to use encryption. They only want to be private if they have something to hide.
Yeah.
Oh, only if you're developing this, it's only going to be used by terrorists. Think of the children. These kinds of arguments.
Right.
And this is something that it really is dominant you really see it in the news, in the news, and then in flashy political rhetoric. Like this is absolutely a thing. I know Christopher Wray came out. He director of the FBI. He's
Yep.
came out and talked about the problems posed by encryption. There's the ongoing debate in the EU about chat control, which is basically kind of an attempt to undermine that, which is something that the German government has been very vocal about opposing, which is one thing that for us is fantastic. That's one reason why we're working from Germany, is because of the strong commitment to privacy and encryption. So for us, we haven't, within Germany, there's not a huge push to get rid of encryption or to harm it. I think there's more, I know there is a lot of criticism. You see a lot of criticism in it towards encryption in the American media. That is something that you do see quite a bit, and mainly falling in line with that kind of the terror line of thought.
And child sexual abuse is always right up there too.
Yeah, and it's almost kind of played like a. I think that kind of argument, like, yes, of course there are people who do bad things with cryptography. Like that goes without saying. That does happen. But just because there are people who are doing bad things with it, there are regular people who want and need this kind of protection.
Yeah.
And that's why for us it's important to provide that.
Yeah.
But it's a difficult conversation to have, and it's extremely nuanced. I don't think it's as simple as saying bad thing happened, nobody can have it.
Right.
And the same with, if you want to go ahead and backdoor, there's no such thing as a secure backdoor. That's something you see the people do talk about. They're like, oh, okay, law enforcement wants to backdoor encryption or whatever.
Yeah.
But
the good guys.
Exactly. It's only the good guys can use this backdoor, and that's completely nonsense. There's no such thing as a secure backdoor. That's why it's a backdoor.
Right.
And so the idea that something like that, like you could contain a vulnerability is it's nonsensical thinking. Even if the idea behind it is in good faith, and I'm not saying it always is, but even if like someone does mean well by that, it's not a secure option. It's not secure to implement a backdoor into encryption. Even if there are different means that people are trying to go ahead and do that in different levels of politics. And I mean, one thing that's also kind of interesting with that, the attacks on encryption, is it's not really that. It doesn't seem to me. It doesn't seem reasonable, especially like in the case of law enforcement. Say you have a suspect who's they've encrypted their computer, or they're using an encrypted messaging app or something like that. If someone is of enough interest, you don't have to break the encryption. In most cases, look at how somebody is going to secure their phone. Maybe they don't even have a passcode on their phone. Like you
Right,
don't know
right.
that. Or say they do. Say they have pretty good. Say someone does have pretty good OPSEC, right? There is spyware like the Pegasus spyware from the NSO
Hmm.
group. You can just send someone a message that they don't need to interact with, and you have full access to what happens on that device. There's
Right,
no need to attack encryption, which is used for legitimate uses like your banking or your healthcare
right,
information.
right. Yep.
So there are legitimate ways that law enforcement can go about doing their jobs. I'm not saying that they should use spyware. I don't want to say that.
Yeah. No, I get what you're
But
saying. Yeah.
it's attacking encryption isn't necessary. I guess that's what I would like to say.
And I think a lot of it comes down to scale too, right? I mean, the things, if we could break everything and record everything, that's different than targeted surveillance instead of mass surveillance, right?
Absolutely.
Yeah. All right, Brandon, looking into your crystal ball, what's the future look like for quantum computing and quantum resistant encryption? Does the math favor the crypto or the code breakers? Do you think there's going to be other big breakthroughs, or is it just going to be kind of slow, steady plotting, incremental improvements to all this?
Ooh, yeah, that's a tricky question. I think it's hard to like again. Yeah, I wish I had a crystal ball. That would be pretty cool. Ponder the orb. But no, I think there will be slow but meaningful progress in the development of quantum computers, and also what because we've seen that in how far these computers have come along so far.
Yeah.
And we've also seen this slow, steady response with the creation of quantum safe encryption, like what Tuta is doing, like what Signal is doing. I don't think these are things that can happen overnight. Of course, something might just happen overnight. I don't know. But I think it's important to keep in mind that mathematics favors the cryptographers. The technology favors the code breakers.
Hmm.
And something that's kind of funny is there's kind of a symbiotic thing going on here. So these mathematicians are working against the technology that their work is also building.
Right, right, right.
It's a very interesting and exciting space. But I think just as there are people who are dead set on trying to undermine encryption or trying to break encryption, there's just as large a set of individuals who are really dedicating their life to creating secure encrypted solutions for everyone and not restricting these things to certain uses or certain organizations. I would like to think that the future favors the cryptographer and not the code breaker.
Well, and I think it's a lot like hacking in that a lot of people think of hacking as a pejorative term, but we want hackers to try to break stuff. We want them to find the bugs first, right? Before the bad guys do, right? In the software,
Exactly.
I'm a software engineer, and we had testers, and their job was to break stuff. I mean,
Yep.
we hired them and paid them good money to take the software that I wrote and try to break it and find not necessarily security vulnerabilities, but they could be, but also just find ways to make it not work right, and so that we could fix those problems before they got out. Right? It's the same mentality. So the people trying to break encryption aren't necessarily the bad guys.
Right.
Right.
Yeah, I don't want to say they're all bad guys. That's
Right.
I don't want
And I
to
don't think
put
you
that
did.
out
I'm
there,
just making that point. It's
yeah.
not like it's a black hat versus white hat, a good versus evil scenario. It's we got. In fact, a lot of the researchers are trying to break it too, right? That's part of what we do. It's part of the vetting process.
Yeah.
So
Yeah, and I mean that's the thing. You're going to go ahead and by having this kind of assault on these new systems, like really putting them through the ringer, like stress testing them. If you don't do that, you don't really know if it's secure or not.
right,
And at the end of the day, that's what everyone wants.
exactly.
Almost everyone.
Right. All right, Brandon. That was great. Thank you so much for explaining that, and thanks again for coming on the interview.
Yeah, cool. Thanks for having me. And if you're ever over in Germany, let us know. You can come visit us in the office.
Oh, I'd love to. Thank you. All right, so I hope at least at this point you have some vague idea of what quantum computing is and what kind of a threat it is to modern cryptography, which really isn't that big of a threat currently. But as we made a point to say during the interview, the real issue here is that these things work. Like, we've shown that this is a viable product. This is something that can be made, and it's just a matter of time until we get one big enough to attack a modern cryptographic algorithm with a certain key length, a certain number of bits. And in the meantime, what's going on is intelligence agencies, for example, and perhaps law enforcement agencies are recording all of our encrypted conversations and messaging and all these things that they can't break now. But if they record them now in encrypted form and they get one of these computers in 10 or 15 years, let's say, it's probably longer than that, but let's say, then they could take that stuff that's encrypted now with the encrypted techniques that are vulnerable to quantum computing and maybe break those things in the future and then decrypt these messages from the past. And maybe there will be valuable information in there. And maybe from a privacy standpoint, there's stuff in there you don't want anyone to know ever. So it's important that we start using the cryptographic techniques that are resistant to quantum computers now, so that all this stuff that's being recorded still won't be vulnerable whenever they finally get around to making a viable quantum computer. Now, for the patrons on Thursday, we're going to go a little bit deeper. We're going to talk about like Shor's algorithm and Grover's algorithm, not too deeply, but we are going to talk about them, what they are. And we'll talk about some other sci-fi kind of stuff like, what's beyond cryptography. Like if you really can do this quantum entanglement thing, for example, you could communicate with somebody at a great distance without actually transmitting data like through the internet or over the air. It just, you change something here and it automatically changes something over there. There's no way to intercept that. So anyway, we talk about a few other things. Then the patrons will get that on Thursday as usual. Brandon did mention Bruce Schneier, as you should know by now. Bruce is going to be my guest for the big episode 400. That's only like 6 weeks away. It's coming up quick. It'll be the Monday right before Halloween, I believe. I've already reached out to Bruce. We have scheduled that interview. We will be recording it soon, and I'm working on my questions for him now. If you have a burning question for Bruce Schneier, feel free to email it to me, or if you're a patron, you can hit me up on Discord. Regardless of what we talk about, it's so much fun talking to Bruce. It's always a good time. So I'm really happy to just sticking with our tradition that I foisted upon him to come back for every 100th episode. So that'll be a lot of fun. One more thing before we go, I would like to encourage you to check out Privacy Guide. I've mentioned them before. They just published an article on Proton Wallet, which has some very interesting points that I think if you're interested in, getting into crypto or maybe moving your Bitcoin from some other wallet to Proton Wallet, you probably should take a look at. It's a good review. It makes some really solid points. And it's always good to get other opinions and get some more details on how it all works. They dug into it a little bit and actually checked out how it worked. So that's a good review if you're considering that. So next week, we've got the news show as usual, and a lot of really great interviews are on the docket. So if you haven't subscribed already, you definitely do that. I don't mention very often, but I should. Obviously, check out the book, check out the blog and the newsletter. If you're looking for more tips on security and privacy, I've got a lot of stuff there for you. Also, next week, I'll be announcing the next phase of my awareness campaign to try to reach more people. I'm going to be leaning on you guys a lot for that. So stay tuned. I'll be telling you how you can help me to help more people. All right, that'll do it for this week. Take care, everybody. Stay safe out there. And until next week, as always, don't get caught with your drawbridge down.